Hi, I'm Vincent.
And I'm Bennett.
Our Air 320 project is on the wind turbine. The simple wind turbine model consists of a rotor, a shaft, and a drivetrain. An aerodynamic torque is put onto the rotor, and there is also an electrical torque input. The mechanics of a wind turbine is highly nonlinear, but it's linearized early in the design process. The left side of this equation represents the dynamic terms, and the right side is all the disturbances and inputs. Kv as a function of t is the electrical torque input, m theta dot is a torque due to the pitch mechanism, and q is the resultant moment due to dynamic and aerodynamic forces.
There are four frames needed to accurately describe the dynamics of a wind turbine. An inertial frame at the base of the wind turbine's mast is used to determine the wind direction and dynamic forces from the movement of other frames. The body frame, shown here as the prime frame, is attached to the housing containing the generator and thrust bearings. The body frame is rotated into the wind so that way the rotor can operate at max efficiency. The rotor frame, shown here as the double prime frame, is attached to the hub that connects all of the rotors. The rotation of said rotor frame relative to the body frame determines the motor speed. Finally, the blade frame is attached to each individual blade and is needed to determine the blade pitch and the principal mass moment of inertia of each blade.
Wind turbines can have closed-loop or open-loop control systems for changing the pitch of the blades. The current pitch position and desired pitch position are sent to a controller.
The controller then regulates the voltage of the blade pitch actuator to change the pitch of the blades. The torque from the blade pitch actuator then dynamically affects the blades, creating a new pitch position. Here is an example PID control law for the pitch of those wind turbine blades. The voltage of the blade pitch actuator, Vt, is dependent on three proportionality constants, Kp, Ki, and Kd, multiplied by the derivative, integral, and normal error between the actual blade pitch and desired blade pitch, Et.
Here are the performance metrics for a wind turbine. The power coefficient is the rotor power divided by the power in the wind, and the tip speed ratio is a blade tip speed compared to the free stream wind speed. A plot of the two is normally used to optimize power coefficient. In summary, a wind turbine is a nonlinear continuous system, though often linearized. It uses a PID controller and a closed feedback loop. The performance metrics are the power coefficient and the tip speed ratio. It takes in a desired pitch angle and a reference pitch angle and outputs the actual pitch angle. The reference we used is Wind Energy Explained by Manuel et al.